Okay, we're continuing our discussion of steel columns. In the last video, we looked at how to analyze a steel column according to the AISC method of analysis. And in this video, we're going to look at design. So the thing about column design is it's not quite as simple as beam design. We don't have a single variable that we can isolate and solve for, like the plastic section modulus. Because we've got a couple different things going on. There are basically two main things that affect a column and how much load it can support. One is the unbraced length. So a longer column is more susceptible to buckling. So the longer a column gets, the more likely it is to buckle and fail. We also have the area. Okay, so a bigger column with a beefier area is going to hold more load. And we also have the radius of gyration. Which is abbreviated with the lowercase letter r. And that essentially is a characteristic of the cross-section that also determines how flexible it is or how likely it is to buckle. So, a larger area makes a weaker column. A longer length makes a weaker column. A shorter length makes a stronger column. And with area and radius of gyration, it's the opposite. A larger area makes for a stronger, smaller area makes it weaker. And with radius of gyration, larger equals stronger, and smaller equals weaker. So because we have all of these different variables, we've got length, we've got area, we've got radius of gyration, we can't just simply algebraically solve for one of them. So basically the design method for a column is guess and check. You may have been expecting something more sophisticated, but that's basically all it is. There is, however, a way we can narrow down our options, and that is to use the basic rule of thumb, and this does not apply all the time, depending on how these three variables are in relationship to each other. The failure stress may be way off from this guess, but we're going to at least initially guess that the failure stress is equal to the yield stress divided by 3. Okay, so typically we're going to be dealing with wide flange sections. That's a common used section for a column that might be made out of 50 KSI steel. So if we're using a 50 KSI steel, then that divided by 3 is 16.7 kips per square inch. So we're going to guess that our failure stress is 16.7 KSI, if in fact we're using 50 KSI steel. But this is just a guess. It's just a starting point so that we can take this stress and then choose an area which will satisfy that stress requirement, and then we will analyze it to see if the column is strong enough or not. So let's put this into practice. Unfortunately, there's not a real good example of this in the textbook, so I've come up with my own example. This is actually from a steel analysis textbook I've used in the past. So we want to select a W14 shape. So there's all sorts of wide flanges, and if we had our choice of any one of them, it might be a little overwhelming. So we're going to narrow our options to just a wide flange that has a depth of approximately 14 inches. Okay, so that's going to significantly reduce our options, and that'll help us out. That'll make this problem a little bit more efficient. Okay, it is a 992 steel, which means that the yield stress is 50 ksi. So we are going to guess that the failure stress is going to be 16.7, and it's going to carry a service live load of 300 kips and a dead load of 100 kips. Now, I haven't mentioned it before now, but there are two different design methods permitted by the AISC. We are using ASD, allowable stress design. The calculations are simpler, and so for this course, it makes more sense. It's what the textbook uses. There is, however, another design method called LRFD, load and resistance factor design, where it's more based on modern day statistical analysis, where we do separate the loads out into live loads, dead loads, and multiply each of them by load factors. The live load factors are greater than the dead load factors. But since we are doing allowable stress design, we don't really need to separate these out. So although it's given the problem gave it to us like this, we really just need to know that the total load is 400 kips. We did look at a beam design problem or beam analysis problem where we had the dead load and live load separated out, and that was because we had to control for live load deflection. We don't really need to worry about that with columns. So the fact that they're separated out really doesn't matter. We've got a total load of 400 kips on our column. That's all that's important. And we have an effective length, actually not just umbrace length, but effective length, KL. So the problem statement has already multiplied the length of the column by K for us. That's going to be 26 feet. Now, it's commonly more convenient to use inches as our unit of length. So 26 times 12 is 312 inches. Okay, so we are going to, as I said, guess that our failure stress is 16.7 ksi. So one of the fundamental basics of strength of materials is that stress is equal to load divided by area. So if that's the case, then if we want to solve for area, then area is load divided by stress. And so we are going to be looking for a column that has an area around 400 kips as our total load, and we are guessing, and I can't emphasize this enough, that this is a guess, 16.7 ksi. I've had some students in the past get really hung up on this number and think that, well, that's got to be the number. That is the stress. This is not the failure stress. This is merely a guess that will get us started so that we can make a choice of which column to choose and analyze. And then depending on our results of that analysis, we may keep that column, or we may need a bigger column, or we may be able to get away with a smaller column. So the results will indicate to us what we need to do. So our area should be in the ballpark of 23.9 square inches, or I'm just going to say about 24 square inches. So again, this is just a guess. Okay, so at this point we will need to look in the appendix for a column with an area of approximately 24 square inches. A W14 column, that is. That's going to reduce our options. So let's go to the appendix. Okay, so I pulled up the appendix, and I'm looking at Appendix A, and I'm looking at the section that has W14, and so I'm going to guess a W14 by, let's see, a 14 by 90. So what do I need to know about a W14 by 90? Well, its area is 26.5 square inches. I also am going to need to know its radius of gyration, the least radius of gyration. So there's Rx and there's Ry. Rx is 6.14 and Ry is 3.7. So the Ry will always be the lesser of the two. So we need to know these numbers now in order to begin to analyze this column. So the first thing we need to do in our analysis is determine the slenderness ratio, KL over R. We were already given the effective length, KL, in the problem statement. Let's see, where was that? Here it is, 312 inches. So that's going to be 312 divided by the least radius of gyration was 3.7. And so that is 84.3. So we need to compare that to the cutoff point of 4.71 square root of E over F sub y, which would be 4.7 times square root of 30,000 divided by 50. 30,000 KSI is the modulus of elasticity. 50 KSI is the yield stress, and that equals 115.4. Obviously, 84.3 is less than 15.4. So that means that we have a less slender column. And unfortunately, given the two formulas, this means that we have to use the one that's mathematically a little bit more complicated. So the allowable load is going to be equal to 0.658 to the power of F sub y over F sub e. And that's an exponent there. My writing is getting a little sloppy here. I should try to be a little neater. Multiplied by the yield stress times the area divided by a factor of safety of 1.67. So we know all of these variables in this equation except for F sub e, the Euler stress. So we need to take a moment to calculate that. The Euler stress, if you'll recall, is equal to pi squared times E over KL over R squared. So that gives me pi squared times 30,000 KSI is the modulus of elasticity. KL over R we have already calculated at 84.3. And then we square that, and that should all be equal to 41.7 KSI is the Euler stress. So now I've got all the variables I need to plug into this allowable load equation of 0.658 raised up to the power of 50 KSI divided by 41.7 KSI. And then after we calculate that, we'll multiply it by the yield stress of 50 and by the area, which was 26.5. And then we'll divide that all by 1.67. And that is equal to, I'm getting 480 kips, which is greater than the 400 kips that is being applied to it. So I'm going to talk a little bit more about this result in the next video. I'm up against my time limit.